Thank you very much, and welcome everyone to this part 2 of our series on the comparison of non-seismic and seismic connection details for precast substructures. This is a continuation. So let me start again, make sure everyone hears. Welcome to this month's seminar, which is a part 2 of the comparison of non-seismic and seismic connection details for precast substructures. Last month in May, we had part 1. And so today's outline is to review briefly what we talked about last month, and in case there are some folks here today that did not join us in May. And then we're going to go into some detail on the connection types and their details and photos of some actual use of these connections. So let's start the review first with the seismic states. And this map shows the boundaries, if you will, for the design categories B, C, or D, which are blue, yellow, or orange on this map. Those are the 3 highest categories, which we would call seismic states. The lowest category, design category A, and this terminology follows the seismic guide specification terminology. The lowest category A would be shown in green here, and this map is set up for the poorest site class E. So if you see a state, for example, on this map that is all in green on this map, then it has only design category A. If your state has blue, yellow, or orange, then you may have the higher categories as well. So continuing. Continuing, we discussed the capacity design concept last month, and the analogy of a chain with non-ductile links and then, let's say, a single ductile link, which is meant to represent conceptually the plastic hinging portions or damageability or deformation permitting portions of the structure, is shown in the top of the slide. And a single ductile link will then render the chain ductile, provided that ductile link is the weak link of the entire system. And if one of the non-ductile links was the weak link, then obviously the chain would be non-ductile as well. So the image to the lower left shows an example of plastic hinge locations that are these intended weak links for seismic load resistance of a bridge structure. And the analogy, I think, also works well if you think about the beverage industry with glass bottles with pry-off tops. Those tops are the ductile link, the bottle non-ductile, and I think everyone's familiar with how that system works as an analogy to what we're trying to do structurally with our bridge substructures. Now, when we go into accelerated bridge construction and start placing various connections between prefabricated elements, then some of those connections may be in these zones where we expect plastic hinging, as shown in this slide, where a plastic hinge might be expected to form at the base of the column, top of the shaft there, and then just under the cap beam at the top of the column. And in this case, we've got moment continuity both at the top and the bottom of the pier in the longitudinal direction for this slide. Now, we may have other connection interfaces in the system that are not adjacent to these plastic hinge zones, and those connection locations are really, their job is to develop the strength, not necessarily the ductility that's required in the plastic hinge zone. So there's a somewhat lower demand, if you will, for those capacity protected or non-ductile, potentially non-ductile connections. So what the strategy is all about choosing where your ductile elements will be and determining what the force will be from those ductile elements and designing the rest of the elements to be able to withstand the forces that are commensurate with those ductile forces. So an example shown here on the left is a cast-in-place substructure with precast girders where At the top of the pier, we're developing an integral connection where we can develop plastic hinging at the top of the column there. So there are certainly capacity protected connections there between the girders and the cap beam and other elements in the superstructure. The photo on the right shows an all precast substructure, again with precast superstructure elements, and the design philosophy is the same there, where we're using emulative construction of cast-in-place construction with this precast bin. Last time we discussed what this might look like from a load displacement relationship, where this particular slide shows a column connected to a foundation that's been tested cyclically back and forth, where eventually we experience spalling, and then ultimately at enough cycles and a high enough drift, then fracture of the longitudinal bars and even fracture of the stirrups or spiral, as you can see in the lower left photo. Now, in our design category D, say the highest design category, we would expect to essentially fully utilize that displacement capacity in the ductility or the deformation capacity in the inelastic range. But in the lowest category, in A, we really expect to have just barely, perhaps a little inelasticity as shown in the red box, but essentially just mobilizing the lateral strength of the system, but not the ductility. If we look at, let's say, another set of columns, in this case, these were precast columns that were connected with Grouted-Duct couplers to a foundation element. And in this case, you see that after testing at that larger drift ratio cyclic testing loading regime, we eventually were able to break the longitudinal bars and achieve ultimately the strength and ductility of the section. Eventually we lost that as you break those bars and start to break the spiral as well. So this is what we're looking for high seismic regions, which stay obviously in design. The specification keeps you a little shy of the point where you're actually breaking the bars, but you do get quite a bit of ductility from these. So we've gone through effort to prove that the details in the laboratory actually will deliver what we need in the field. Now, when we talk about a connection itself, the connection might be thought of as just the interface, the dashed black line there, and this could be in an area, in this particular case, where we have a plastic hinging or energy deformation, energy dissipating zone at the top of the column in the yellow oval. And obviously the connection between the column and the cap beam is right at the interface, where we also expect to see the energy dissipation going on. So where the hardware, so to speak, is placed and how the details are put together in this connection may have a bearing on how well the connection performs. So in this particular slide, we're showing the hardware where the bars coming out of the column may be connected with, let's say, a grouted duct or a bar coupler up in the cap beam. Those hardware elements are put into the cap beam where the inelastic demands are somewhat less than they would be down in the energy dissipation zone itself. And we'll talk a little more about this in a later slide. So what's special about seismic applications? Well, certainly we expect that we're going to need continuity of load path under load reversals. So that means we need to be able to transmit lateral load from, let's say, the point of generation of that, which would be the inertial mass points in the structure, superstructure, for example, down into the foundation. We also, for higher seismic locations, we're going to need to develop cyclic inelastic deformations, and the maximum forces, or in this case likely the moments, the way we think of this, would potentially occur where we'd like to connect prefabricated elements. We'd like to transport these elements as single linear elements, and therefore the connection location is often the same point where the maximum moments occur, and therefore the plastic hinging action also occurs. So this is the challenge for precast substructure construction. And then certain element material behaviors may cause rapid loss of cyclic resistance, and that would be local buckling of say, reinforcing bars, for example. So this occurs typically, if things are well detailed, after you've achieved large inelastic deformations, and once the longitudinal bars, after being stretched in tension, then start to buckle in compression, you eventually rapidly lose their capacity and fracture the bars. As I said earlier, we try to stay just shy of that point with a bit of factor safety in terms of deformation. Now, additionally, strain concentrations can reduce the inelastic or deformation capacity, and that is what I was alluding to where I said we want to keep the hardware out of the energy dissipation zone if we can. That reinforces point 5 here, which is that detailing is certainly important. Now, continuity of strength. In the high seismic areas, inelastic ductility is certainly required. That means we're going to deform the structure into the inelastic range with attendant damage, and thus, all these members that are connected have to have adequate strength, not only at the plastic hinging point, but throughout the system, so that we can form the intended plastic mechanism. That is, you don't have unintended weak link somewhere else in the system that might be a weak non-ductile part of the chain that we discussed earlier. In lower seismic areas, continuity, this would be design category A, for example, continuity of the strength is still required, as we're still trying to mobilize essentially the full strength of the member, but not the ductility. We don't need that inelastic deformation capacity. And in low seismic areas, we're still meeting, let's say, minimum lateral or minimum member strength requirements, and then that will lead to a lateral capacity that we can mobilize the strength of, let's say, the column, the cap beams as a lateral system. The same would be true for, lateral design, say, for wind. You need to be able to certainly resist those lateral loads, even though you may not be counting on inelastic deformation capacity as we would in the higher seismic areas. So the logic behind detailing for the lowest category is that at a sufficiently low seismic hazard, then the structure has an inherent ability to tolerate, that develop the lateral strength and perhaps tolerate minimal inelastic action without any special detailing. But we will need to provide connection forces depending on how we articulate the structure, for example, to prevent unseating, or provide adequate support links to prevent unseating. And there's several strategies that can be used here. But the idea is that potentially, even in the low seismic category, the structure may see a small amount of damage, but would survive, consistent with that performance. And what we're talking about here, where we're permitting damage in, say, the design earthquake, is really the sort of the general category in terms of use for the structure, not higher operational classifications where you may want immediate use of the facility after a design earthquake. Then we would go to a higher performance standard, sort of a special case that would require considerations beyond what we're discussing here today. Now, the detailing and continuity, we showed this slide last time, and we want to review this, that we show a column here connected to a crash wall at the base, a pier cap at the top. Certainly, if this was in a high seismic area, we would want inelastic ductility of that column, an adequate strength of the connected elements. So we'd have, let's say a minimum amount of spiral that would confine the column, minimal strength of the column longitudinal bars, and therefore moment capacity. But in the lower category, we don't need to provide as much confinement. We still have some, and so there's some prescriptive minimums there. We actually have a a split in the design category A, the high A, low A, and in high A we have minimal transverse steel required. In low A there is no seismic minimum transverse steel. So the idea is to avoid unintentional weak links and to avoid unnecessary and unexpected damage that would not render our structure life safe, if you will. In other words, it would be a potential collapse hazard. So we're trying to avoid those sorts of weak links. Now this particular column was set up for design category A, so you see the hardware here for the grouted bar couplers or splice couplers. See the hardware in the column at the base, and this is okay in the lower categories. You see the same hardware shown up in the cap beam at the top, out of the potential plastic hinge zone. It's a good detail, and these locations are set up really to facilitate the easiest constructability of grouting of this system and handling of the elements. Now, there is research that's underway looking at specifically this question of where the grouted splice couplers are located and whether it's actually permissible with some adjustment to the design procedures to put the splice couplers up into the plastic hinging zone. Right now that's in the higher category, not a practice that you necessarily want to use, but we think that with proper justification and testing that's going on right now in a couple of places, University of Nevada, Reno, and the University of Utah, we may be able to develop some design procedures that then would permit this and therefore allow this type of construction. So let's move now to the connection types and look at some applications and details of the different types of connections as we've categorized them here. And the categorization is taken from an NCHRP report, which was a synthesis on accelerated bridge construction connections in moderate to high seismic regions. This is report 698. We gave you a reference to this in the May webinar, and I'll give you a reference URL at the end of the presentation back to that, but I'm not going to repeat all the references here today. But the categories that this report put the connection types into are listed in the bullets here of bar couplers, grouted ducts, pocket connections, member socket connections, then integral connections, and this would be, for example, connections of superstructures to piers, and then a final category of emerging technologies. Now, as we go through this next series of slides, there are a number of these connection types that have been tested in the laboratory, deployed in the field. We know they're constructible, and therefore we could say they're totally ready for prime time. There are other connections that have been conceptualized. The testing behind these, say in the laboratory of large-scale or even full-scale elements, has not been completed, and so that could be an impediment certainly to the use by many folks. So until we have testing completed for all those, those type of connections, and those are some of the member socket connections and some of the integral connections, those don't really enjoy the same thoroughness of development that the previous connections do. So this is an evolving technology as we conceptualize different types of connections and move to deploy those in the field and eventually test those appropriate in the laboratory to prove that they work. This doesn't stop one from potentially doing a proof set of tests on a particular job or project to fully vet the performance of the system. And then finally, the last category is emerging technologies, which are things that are really under development and not ready to deploy yet into the field, but may be something in the future that will provide additional flexibility for accelerated bridge construction. So let's start through the connection types now. First are the bar coupler connections. I think many of you have seen these. Shown on the left is a conceptual illustration of how these would be connected. This is very similar to the column and pier cap that I showed in the earlier slide in the drawing. And in this particular case, you'd have a mechanical coupling device, a cast steel element that then bars are inserted into, dowels as they're called in this slide, and then grouts placed inside around the bars. It's highly confined. You can develop the full strength of the bars in this very short length, although very short is a relative term. For the larger bars, these mechanical couplers can become relatively large compared to, say, plastic hinge zones. So the attendant stiffness of the combined bar mechanical coupler grout element in a plastic hinge zone can alter the deformation capacity and kind of the distribution of curvature over the column in a plastic hinge zone. And so until fully proven, that's why we're saying these couplers and this hardware should go into the capacity protected adjacent element if at all possible, and certainly in the higher seismic categories. So this slide shows an example of that type of system being deployed in a design category A application in Massachusetts with bar couplers. There's the crash wall. This is actually the bridge that we used the drawing from in a couple of slides previous. And you can see the dowels stubbed out of the column in the lower right photo where they're lowering the pier cap over those dowels. And this really requires, this type of construction and these type of couplers requires a lot of care on the part of the fabricator and the contractor in terms of coordinating the positions of those dowels, the tolerances, to ensure that all this fits together. The bar couplers have limited amount of tolerance, but as long as you coordinate this, and this has been used in the vertical construction industry for many years, that this type of construction is certainly buildable, but it requires some attention to the details of the geometry. Now, a different type of connection, but trying to achieve the same goal, is the grouted-duct connections, where you have reinforcing bars then grouted into steel, like PT duct, that is placed into a precast element as a cat beam, as shown in this slide, where you see in the upper two photos examples of testing that was done as part of the 1274 project, University of California in San Diego and Sacramento State. And then in the lower photo, you see an application of this from the Washington State DOT of first stage or lower stage cat beam that's being placed over dowels. And in this case, the number of bars is, this was a contractor proposed change, so the number of bars in the columns stayed the same. But in general today, what we're trying to do is use fewer bigger bars with bigger ducts to minimize the fit-up that's required between these elements. And the grouted duct connections have the advantage of you can provide a bit more space between the bar and the duct, giving you more fit-up tolerance. And you can see in these photos just what's required in the joint region in terms of passing reinforcing bars in the cat beams through that region of couplers or the ducts. And you can see that in certain parts of the curve of the circle of the ducts, you can pass no bars at all. Now, in the higher seismic zones or categories, there's quite a bit of prescriptive confinement steel that's required in these joint regions to keep the joint region from unnecessarily cracking and becoming a flexible and unintended weak link. In the lowest category, that confinement is not required, so that you have a little relief in terms of congestion and reinforcing steel for such connections. This shows another application of the grouted duct, in this case energy dissipating connections, where you've got a column shown in the middle photo there, and then the cat beams placed over these bars. This is a two-stage cat beam, so the bars extend through the first stage and into the upper stage, as shown in the graphic to the right. Also shown in the slide is, in this case, we have 4 columns. There are 2 cat beam pieces. Those were grouted in the center. We wanted the gravity load of the cat beam to be controlled, statically determinate as you place it. It also helped us save weight of that cap beam. You've got a splice in the center with a lot of bars, again, minding the detailing. This went together quite well, but it does require careful attention to detail. The next series is pocket connections, where now you have a blocked out pocket in a cap beam, and the pocket could be created by a corrugated steel tube that can also double as confinement around the concrete that will be placed in the center as you extend bars from the column up into this pocket. So the next slide shows some photographs of testing of this type connection. It's really a nice connection in terms of the way the steel is put together in the cap beam. You can see the placement of just plain concrete into that center pocket. You can see the detailing on the side there in the cage at the top. So this is a type of connection that's been conceptualized, tested in the laboratory. I'm not aware that it's been deployed on any or many different applications. It does have a challenge in that you have to support the cap beam on some sort of, typically a collar or some sort of false work above the column. As you could imagine, you don't have the concrete in the center of the joint region, which allows you to place shims, which the Grouted-Duct connection does. So that's an advantage that the Grouted-Duct concept has over this pocket connection. But there are many ways that you could connect these elements. And again, the seismic philosophy is the same in all, that we're trying to develop emulative construction of reinforced concrete where we're still able to force plastic hinging in the column and then restrict damage from occurring in the cap beam, while at the same time making it constructible. The next category is a member socket connection. Shown here, two different types. One is a socket with a member that goes into, say, a cast-in-place footing. The other on the left is you could have a precast footing with a block out that then is grouted up. So the one on the right, again, has been tested and deployed. The one on the left has actually been deployed but not tested. So it's an idea. It works. It's worked when we've used it in the past, but it's not something that we can point to a lot of laboratory data on. So this photo shows an example of the member socket energy dissipating connection. This is from the Highways for Life project, or similar to Highways for Life project. This was on a project that we had where we used 14 of these in a single combined footing. See, the plastic hinge zone would be up by the upper person that has his hand on the column, and then the socket is down into the foundation steel, which is being tied at the moment here. Since this column is straight, this shows that system of connections where the column now has headed bars on it to affect force transfer between the column steel and the footing, relies on confinement of the reinforcement in the footing around the column in a corrugated interface. This actually produces a very good force distribution within the footing. We think better even than bars that are typically turned out in cast-in-place construction. This shows a photo of testing of that type of column in the laboratory where we actually did no damage to the footing, achieved the plastic hinging performance that we wanted in the column, and the test was done with the base of the footing up off the floor, so we also proved that the column did not punch through the footing. So this worked quite well. We can also use the same concept with a drill shaft. This shows how the shaft might be constructed. The transition zone at the top, place a precast column, the same details as for the cast-in-place, but with appropriate lap splice, and then place the transition zone concrete around that precast element. We tested 3 of these columns in the laboratory on a 40% scale. We pushed the the diameter ratio between the column and the drill shaft. So we've got a kind of a minimum size drill shaft here, and then looked at different confining steel ratios and distributions of steel, and intentionally had one that was very light, and you see that in the center photo where we broke away the transition zone or the collar of the shaft. So we got good data on how much confining steel is required here, and this is covered in the Highways for Life project reports, which I gave you a reference to last time in the May webinar. Now moving to member socket connections that have been conceptualized and used but not tested, show this example used in marine construction where we had steel piles with collars welded on them, as you can see in the left-hand photo, and then precast caps placed over and grouted. This system has worked well it hasn't been tested in an earthquake, but it's worked well for all the other load combinations that have been applied to the actual system and is done well in service. Integral connections. These are very commonly used in some states and are used to affect continuity at the top of the pier to the superstructure so that you get additional lateral resistance capacity out of the bridge system than if you had just a plastic hinge or continuity at the base and then, say, a bearing at the top. So again, these have been deployed, they've been conceptualized, but because of the in design, but because of the size of these connections and the complexity cost of testing longitudinally, there are only a handful of tests that have ever been done that are on very specific, case-specific details with dapt ends and post-tensioning and that sort of thing across the interface. But a typical application is shown here. This was on the Dumbarton Bridge in the San Francisco area, where this is a capacity-protected connection. Got continuity of steel across from the girders, the base, and at the top. That steel's not been placed quite yet. You see the precast panels to the side. This was a kind of a tub beam that then was filled with concrete. The plastic hinging zone would be below this cap in the columns. You can see the column cages as they extend into this connection to the cap beam. This slide shows conceptually a similar arrangement for the Highways for Life project, where we've got the two-stage cap construction, place a precast cap, then place girders on that, and then use a cast-in-place second stage at the top where we integrate the steel together. And so I want to walk through a series of slides here that help you understand the force transfer and some of the nuances for this two-stage cap construction and the capacity protection design that needs to be done. So this shows, again, a bridge that has a fully precast substructure. The column plastic hinging region is where the red arrow is in the column. And under longitudinal movement of this bridge, we would need to develop the adequate moment transfer and force transfer up in the superstructure where the forces turn the corner from the cap into the superstructure. And that is a higher moment, actually, than the column overstrength moment because of the additional length of the first stage cap beam down below the superstructure. But the joint region is really up in the superstructure and the projection of the superstructure depth with the cap beam below. So let's look at that in a cross-section here. You can see the entire configuration here. The plastic hinge is that red oval down at the base. The first stage drop cap, in this case, is transmitting those forces up to the intersection of the girders and the vertical projection of that cap beam. And it's in that center zone with where it says joint forces resolved in this region that we've got to transition from the forces in the vertical steel coming out of the column and the cap beam to the horizontal steel that's in the girders and topping. So, for example, precast pre-stressed girders, we'd have strand or some deformed bars, but but strand also extended out of the girder, so you'd have strand chucks, for example, in place. You need overlap between those to be able to develop the strength of the girders in positive moment. In other words, at the tension at the bottom of the girders, and then at the top, you've got the topping steel that can provide quite a bit of capacity for you. This just shows you an example of what has to be considered, and we do have a design example in the Highways for Life reports again. Now, looking at this same connection in the other direction, you see that there's kind of a spread as you go up from the column through the first stage cap, that's with the depth D sub S1, to the upper level, which is the cast-in-place portion and where the girder projections would connect, and that's in D sub S2. And so we've defined an effective width. Again, this is a way to do it. It would be great at some point to have a test of this to prove the actual be effective, but what's being proposed here is a one-to-one spread up through that lower stage to the center line of the upper cap. So then that defines the area where reinforcing steel is effective in this joint transfer, force transfer. Looking down on the same connection, even with the skew, you see that B sub F, that the B sub F is in the center, has two girders in this particular case that it captures, and so 2/3 of that moment is assumed to be resisted within that effective width, and then the other 1/3 of the moment is resisted beyond in the adjacent two girders. So you have torque that's required, and sort of you want to think of it as a strut and tie mechanism that has to get from the column, between the column and the girders to transfer these forces. Again, a design example in the Highways for Life reports. Now, lastly, I'd like to finish off with a bit of discussion on emerging technologies with a couple of examples that are out there. One is the idea of sort of a plug-and-play, a replaceable plastic hinge zone component system. This is a concept that Caltrans has been looking at and testing, where you have an intentional weak link of bars that are between these couplers, and those bars are the ones that are intended to yield. The bars outside of that coupled region are stronger than the bars in the center, and so you have an intentional weak inductal link. This satisfies our design philosophy. This is a precast column, and then the outer shell is cast after placement of all the steel here. One of the challenges, obviously, with this is we have tight tolerances, not only in the kind of the cross-sectional dimension, say X, Y, but also in the vertical dimension of tolerance of the length of those bars and the placement of those couplers. So this is potentially something that could come down the pike, or a variant thereof eventually. So this is in the emerging technology realm. Likewise, and another system that shows great promise, particularly for the higher seismic areas, is what's called a hybrid connection, where the column is reinforced with a combination of deformed bars and post-tensioning, unbonded, or in some cases there's even examples of sort of bonded at the end and unbonded in the center. This system performs analogously to the child's toy that is connected with elastic bands, and you push up with your thumb from the bottom and a little figure will fall over, and if you release your thumb in the spring, the figure pops back to an upright position. It's very similar to that type of toy. But this is a serious system where the reinforcing bars can provide the energy dissipation, the unbonded post-tensioning provides deformation capacity, and the combination of those two reinforcing details provide this sort of flag-shaped load displacement or force displacement relationship that's shown in the upper right, where you see what looks to be some ductility. That's the area within that flag. The system has very good recentering capability, which is one of the advantages. So instead of being yielded and staying in a deformed position, it comes back to essentially the starting or vertical position of the column. This has been used in buildings. It's been tested a number of different places. Some of the concerns right now have to do with durability of the system, and then being able to make sure you have the appropriate post-tensioning force in relatively short lengths of members at any time over the life of the structure. So there's some challenges with using this system, but I think eventually we may get to the point where these are deployable. And so I'd like to wrap up the presentation here with a concept which we've termed technology readiness level that was actually adopted from initially from NASA. And the idea is applied to accelerated bridge construction here is you've got TRLs, or technology readiness levels, starting from 1, which is the concept exist, all the way up through 9, which we've had adequate performance in a design earthquake. And along the way, you have things like seismic testing, ability to calculate strengths and deformation capacities, and then design and construction guidelines. And so the systems that I just went through, from bar couplers to emerging technology, are shown in this series of plots. And to the right of the technology readiness level, we show, admittedly, sort of just an estimate, but it's a way to think about this, of percent development complete of each of these levels. And so as part of the 698 synthesis report, we developed these technology readiness levels with the bars at the percent complete levels that are shown here in gray. And since that report came out a couple of years ago, there's been additional work, as I mentioned, with, say, bar couplers that has been done in the interim and is nearing completion now. And so I'm showing some red blocks there that fill in some of the blanks that we have with bar couplers, where we had done some testing of components or had been analyzed, but we hadn't done all the testing that we needed to do. And so we've kind of backfilled or infilled that testing void and now have good data on how those perform. In closing, I will say also that there is a NCHRP project, a 12102 project, that's just currently getting underway, and that'll be a 27-month project. But the idea is really to address, for that project, to address level 7, design and construction guidelines for this accelerated bridge construction connection technology, and try to develop, to the extent we can, appropriate design and construction guidelines that would be in one place for the systems that have adequate testing completed. Now, there'll be some additional testing as we move forward that will be required to fill in behind the 12102 project, but the idea of that project is to capture in one spot what we have to date. And so that's just now getting underway this month. So with that, I will wrap up and take your questions. So thank you.
All right, thank you, Lee, for such a great presentation. At this point, I'll turn the screen to Ben Bierman, who is going to be moderating the question and answer period. Ben? Ben,
can you hear me okay?
Yes, yes, we do.
Okay, all right, folks, we received about 20 pre-webinar questions and about, I'd say, half a dozen during Lee's presentation. I grouped them. We have a group from testing to implementation. We have another group called resources, questions that go over design considerations, cost, future research, and constructability. So, Lee, I believe Mike Kumo is going to join you with the Q&A session as well?
Yes, that's correct. Yes, this is Mike Kumo from CME Associates. And many of you may recognize his name. He's been involved with a great number of the federal highway documents that have been put out there in terms of this technology. So we welcome Mike.
Thank you, Lee.
Okay. All right. Okay, Mike and Lee. We'll go ahead and start off in the category testing to implementation. The first question, are there any pre-qualified connections for accelerated bridge construction?
Well, this is Mike. One of the things that any connection has to meet is the requirements that are in the AASHTO. For, say, any bar coupling connection, you need to develop a certain amount of strength. In the current AASHTO specifications, it's 125% of the specified yield strength of the bar. The ACI code has has a higher level of coupler that may eventually find its way into the AASHTO code, which is 100% of the specified tensile strength of the bar. In addition, though, Lee mentioned quite a few research projects that have been undertaken to test these connections to develop design equations, for instance, the Grouted post-tensioning duct connections. So when it comes to bar couplers, we typically follow the AASHTO requirements of a typical mechanical connector.
Okay, and what states, are they starting to incorporate details or acceptable details into some of their bridge manuals?
Yeah, I'll start with this one too. As Mary Lou showed, Massachusetts DOT has issued ABC details in their bridge manual, just recently was released. Some other states have referenced federal highway documents and allowed those by reference to be used in this state. And I think as time goes on, we'll see more and more states adopting details. There are a number of details out there. As Lee showed, for any one connection, there's options available. And we anticipate states will evaluate each one of these details and connections and pick the ones that they feel most comfortable with and adopt them into their bridge manuals as time goes on.
Okay. And it looks like through Lee's presentation, perhaps the only connection shown in, I believe, in the group of 6 was that bar couplers they're provided by a supplier. Are there other connections that are also out there on the market that are available by suppliers? I would say we'll call them proprietary-based type connections.
Yeah, well, as I said before, you want a connection that meets the AASHTO requirement for mechanical connector. And there are a number of companies, a number of different connectors that meet those requirements. The key is to get a coupler that fits within a precast product that can work with a precast product. A number of the connectors are good for conventional cast-in-place construction, but working it out where you can have a piece cast into one of the elements like the grouted bar couplers or the grouted post-tensioning ducts. So there are a number of options out there, and as you saw the research photograph that Lee showed of the repairable column end that Caltrans is looking at, there's another example of a proprietary bar coupler that's out there that meets the AASHTO requirements that can be used for some of these connections.
Okay.
And you will find that some DOTs, in particular Caltrans, with their requirements for what they call an ultimate splice, they have lists of, at least from their perspective, pre-qualified products for the different levels of couplers. So there's information out there that they've posted that's available, in whether a state would, pick that up and use it, it's up to them, but it's certainly there's information out there.
And one thing I'd like to add, the key thing to understand about all these connections, and Lee touched on this quite a bit, is there are 2 different design methodologies currently in play in the AASHTO specifications. There's capacity protected and displacement connections. The guide specification, which most of the high seismic states are moving towards, are looking at the displacement methods. So as Lee pointed out, made it very clear, is that you need to look at displacement in addition to strength. A lot of the couplers that have been used to date, like the grouted sleeve couplers, they work for strength, but now that we're moving towards displacement-based methods, the deformation curves for the hinge zone becomes an important part of the equation, which is why the research is underway now to get a better understanding of how the performance of those connections are in a displacement-based method.
Okay. We got a question from our friends that deal a lot with the building industry, and I want to read this one to you. It's pretty interesting. In the building industry, we would like to see plastic hinges formed in the beams rather than in the columns for safety reasons. What is the rationale for developing plastic hinges in the columns? And of course, their concern there is bridges collapsing without giving any warning or pre-warning.
Yeah, that's a good question. Lee, you want to start with that one?
Yeah, I'll start with that one. In the building industry, you're typically dealing with multi-story structures where one of the things we learned many years ago in 1971 is we don't want to have a weak and soft story that all the energy dissipation can be concentrated in and lead to a collapse. And so there's been a real effort in the building industry to put their plastic hinging and deformation compensation elements, if you want to call them that, in the beams. For bridges, which are typically a single story, if you want to think of them in the story terminology, the superstructures are in fact well engineered for longer spans. This is in horizontal construction. The superstructures, therefore, are not particularly tolerant or commensurate with putting energy dissipating details like plastic hinges into the beams. The portion of the structure that can tolerate that is the substructure, so we put the plastic hinges into the columns there, but also check things such as P delta effects, the deformation levels. We keep those controlled, but it's, I think, a much more reliable system and cost-effective system to put plastic hinging into the substructure. And with regard to bridges collapsing, typically in earthquakes, typically where we've seen that, those are bridges that either were not designed to what we would be using in a modern design code like the AASHTO guide specification or the AASHTO LRFD bridge design specification. So those typically represent an older type of detailing that we've moved beyond. And in the unusual cases of, say, a double-decker, that double-deck viaduct, for example, that's a pretty specific structure that requires development of seismic qualification procedures on its own merit, so not really covered directly by the AASHTO document.
What I'd like to add to that, too, is even if you look at, say, an open-frame pier bent for a bridge, you might say that, well, we could design the cap across the top of the bent for hinging and not have the column go to hinging, which is true for the transverse direction. You can't design it like a building. However, bents are two-dimensional structures per se, and then for when you look at seismic in the other direction, it's inevitable you're going to get a plastic hinge developing in the column anyway in that direction. So if the hinge is going to develop, you might as well deal with it in both directions, which is commonly done. But Lee gave a very good explanation of the reasoning behind the two codes.
And if the person's interested in additional information on that, there's some great federal highway documents out there that on seismic design that can be found online that would walk through more of the details of that philosophy and approach.
Okay. Let's stay in the design and the philosophy. There was a question, can one design a structure to be fully elastic in a seismic event to avoid detailing for plastic behavior?
The answer is, I guess you can. It's cost prohibitive to do something like that. The amount of strength required to meet the seismic demand is significant. Lee, I guess you would like to add to that as well.
Sure. It's rather like you think of your house and your circuit breaker system. If you know exactly all the power draws in your house that you're going to have, I suppose you could avoid a circuit breaker system. But with earthquakes, similar to the house power analogy, you may have earthquakes that are larger than the design earthquake. And so if you design just elastically, if you had just a bit larger earthquake, you may then find that you had unintended consequences of weak links that you hadn't anticipated, types of failure that you didn't prefer, say shear failure versus flexural yielding. And so part of the strategy, in addition to being cost effective, as Mike outlined, part of the strategy is to define certainly for the higher seismic zones, a fused system where the internal forces in the system under earthquake loading are controlled and definable.
Hey, since you mentioned cost effectiveness, there was a question regarding that. How much premium cost, perhaps in percentages, is required for the high seismic regions versus the low to medium seismic regions? Is it much of a premium from going from one to the other?
I think that's a difficult question to answer because we see in so many parts of the country, like in our area here in the Pacific Northwest, you get used to building, and the contractors get used to building these systems, and they get techniques developed for putting them together, and you're really talking about how you detail the reinforcing in the system, and particularly now with the seismic guide specification, the designer has more control over the actual strength required of the column. So you're really talking about changing a bit the reinforcing content and details, which isn't a huge dollar amount of the bridge. So there's some premium. I hesitate to throw a number out there of what it is. It's very dependent on the type of bridge that's being used in a given location. We know different DOTs in different areas of the country have their own preferred types of structures, and that cost premium would vary by the type of structure. And Mike, you might want to add to that.
No, I think I think you covered it well.
Yeah. It's tricky going from one location to the other. Mm-hmm. This question came up, Lee, when you were showing the slide that has the spreadsheets, the technology readiness level of different tables. The question, let's see here, it says, appears that all the tests were done under lateral loads only. Have there been any studies, analytical or experimental, on the combined effects of axial and moment and torsion? For example, like applications that include outrigger bends.
Well, typically the testing that's done, say the lateral loading testing, will always have an appropriate level of axial compression, dead load, for example, or permanent loads. And so we're always in the testing having an axial load that is representative of what you would see in a structure. And in terms of torsion, for example, the example being the outrigger bent, but could also be a multi-span bridge with let's say continuous or integral substructure and superstructure on a curved structure. You could have torsion in the columns. I know that in some of the shake table tests that have been done in recent years at Nevada Reno, they found there was torsion on the columns. They cracked in torsion and were very flexible, as we know that cracked concrete under torsional loading is quite flexible. So I think there's probably some, over the years, there will be some improvements based on those tests. That was a curve bridge test. In terms of outrigger bents, there have been some specific tests done on outrigger bents and specific details developed for outrigger bents that really are beyond the scope of what we were talking about today. And if people are running into that sort of situation, then dig through the literature to find what's been done. But those are pretty case specific, and in fact, the tendency with outriggers have been to build a much beefier and potentially post-tension. A number of retrofits and new structures have been post-tension in terms of cat beams for outriggers to produce a more definitive plastic hinging mechanism that's controllable in the column. So there's information out there.
Okay. All right. Well, we're kind of running up against our time. Adirad, I don't know. Do we have time for one more?
Maybe one last question, Ben.
Okay, we'll go straight to the constructability question. Tolerances. Are there tolerances recommended for the male to female connection, specifically when you're taking a connection between a pier column and a precast pier cap?
Ben, it's Mike. I could jump into that one. It's tolerances are near and dear to my heart because to date, all problems that have happened with prefabricated projects in the country can almost always be directly attributed to tolerances. The answer is yes, there are. The Grouted couplers shown. PCI tolerance manual does include details for those couplers, approximately plus or minus half an inch, which, as Lee said before, is a relatively tight tolerance for bridge construction. The PCI Northeast Bridge Tech Committee has also issued tolerance detail sheets for typical precast elements as well. So there are tolerances out there. Again, the PCI Northeast is a good opportunity to look into some of these, or the PCI tolerance manual is published for the national document is published for precast products.
Okay. Well, folks, we're going to have to wrap up our Q&A session. There's other questions that were asked, and we'll go ahead and work on those and try and get those posted onto the website. So, Adirad, I'll go ahead and pass the baton over to you.
All right. Thank you, Ben. Thank you, Lee. Thanks for the two great webinars last month and this month. It's we're going to have an archive of these the two webinars. It's a very valuable information for to the profession. So thank you. Thank you, Mike, for helping the panel and everyone else that helped to bring these two webinars to you. So with that, we'd like to conclude the webinar and hope to have you for our next webinar, which is going to be in July on performance of the ABC bridges. Thank you.